In this presentation, we are going to discuss the differentiating and integrating power series and modeling with Taylor series. This discussion, we are going to have uh, methods for finding power series for derivatives and integrals of functions. And we will discuss some practical methods for finding Taylor series that can be used in situations where it's difficult or impossible to find the series directly. So let's start with differentiating power series. Um, we begin by considering this problem. Suppose that a function f is represented by a power series on an open interval. How can we use the power series to find the derivative of f or of the function on that interval? So um, the solution to this problem can be motivated by considering the Maclaurin series for uh, sine x. So for that, we have, um, let's say you have sine x would be equal to x minus you have x cubed over 3 factorial plus you have x to the fifth power over 5 factorial minus x raised to 7 over 7 factorial plus so on. Okay, in the interval, you have x is greater than negative infinity but less than positive infinity. So of course, we already know that the derivative of the sine x is cosine x. However, we are concerned here with using the Maclaurin series to deduce this. The solution is easy. All we need to do is differentiate the Maclaurin series terms to differentiate the Maclaurin series term by term and observe that the resulting series is the Maclaurin series for the cosine x. So what we are going to do, how we're going to present that one. So remember that in the previous example, the sine x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to 7 over 7 factorial plus so on. Now we are going to differentiate that one. Then we can obtain the, okay, so you have d over dx of, you have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x raised to 7 over 7 factorial, okay, plus so on, would be equal to, you have 1 minus 3 x squared over 3 factorial plus 5 x raised to 5, not 5 raised to 4, raised to 4 over 5 factorial um, minus 7 times x raised to 6 over 7 factorial plus so on. Okay, and if we are going to simplify that one, that would be 1 minus, okay, so this is x squared over 2 factorial plus this would be 5, so you have x raised to 4 over 4 factorial minus x raised to 6 over 6 factorial plus so on. And this is actually the Maclaurin series of cosine x. Okay, So that is how we can find the in the integral of sine x. That's why sine x is the integral of sine x, and not the integral. The derivative of the sine x is equal to cosine x. Now let's have another example. Let's say we are going to find the derivative of e raised to x. So uh, taken in the previous example that we had, so we know that e raised to x is actually equal to 1 plus x plus you have x squared over 2 factorial plus x cubed over 3 factorial plus x raised to 4 over 4 factorial plus so on. Now, since we're going to get the first derivative of this one, then let's get the derivative. So you have d over dx, and here this must be d over dx. Okay, which is actually equal to, you have 1 plus 2 times x over 2 factorial plus 3 times x squared over 3 factorial plus 4 x cubed over 4 factorial plus so on, which is just equal to 1 plus x plus x squared over 2 factorial plus you have uh, x cubed over 3 factorial plus so on, which is equal to e raised to x. So that's why the derivative of e raised to x is just equal to e raised to x. So the preceding computations suggest that if a function f is represented by a power series on an open interval, then the power series representation of the first derivative of f rather, on that interval can be obtained by differentiating the power series for the function f term by term. So this is stated more precisely in the theorem. So what is the theorem? So the theorem, okay, differentiation of power series, suppose that a function f is represented by a power series in x minus x sub 0 that has a non-zero radius of convergence r. That is, you have the function f of x is equal to the summation of c sub k times the kth power of x minus x sub 0 from 0 to infinity, with the interval x is greater than x sub 0 minus r but less than x sub 0 plus r. Then the function is differentiable on the interval, the open interval, you have x sub 0 minus r to x sub 0 plus r. If the power series of the power series representation of f for f is differentiated term by term, then the resulting series has a radius of convergence r and converges to the first derivative of f on the interval. You have x sub 0 minus r to x sub 0 plus r. That is, the first derivative of f of x is equal to the summation of the derivative, or the d over dx, times c sub k times the quantity x minus x sub 0 raised to k from 0 to infinity at the interval x greater than x sub 0 minus r but less than x sub 0 plus r. Okay, so this theorem has an important implication about the differentiability of functions that are represented by power series. According to the theorem, the power series for the first derivative of f has the same radius of convergence as the power series of f, and this means that the theorem can be applied to the first derivative of f as well as to the function itself. However, if we do this, then we conclude that the first derivative of the function is differentiable on the interval x of 0 minus r to x of 0 plus r. And the power series for the second derivative of the function has the same radius of convergence as the power series of the function and the first derivative of the function. So we can repeat actually the process, okay, applying the theorem successively to the second derivative, the third derivative, or to the nth derivative of f. Um, to conclude that the f has different derivatives of all orders on the interval x of 0 minus r to x of 0 plus r. So we could have this theorem. So if a function f can be represented by the power series in x minus x sub 0 with a non-zero radius of convergence r, then the function has derivatives of all orders on the interval. You have the x sub 0 minus r to x sub 0 plus r. In short, it is only the most well-behaved functions that can be represented by power series. That is, if the function f does not possesses the derivatives of all orders on an interval or on the open interval x sub 0 to r to x sub 0 plus r, then it cannot be represented by a power series in x minus x sub 0 on that interval. Okay, so let's have integrating power series. Since the derivative of a function that is represented by a power series can be obtained by differentiating the series term by term, it should not be surprising that an antiderivative of a function represented by a power series can be obtained by integrating the series term by term. So, for example, we know that sine x is an antiderivative of cosine x. That is from previous calculus subjects that you had. So here is now these results can be obtained by integrating the Maclaurin series for the cosine x in term by term. So we have so you have the okay. So you have the integral of cosine x dx is equal to the integral of you have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x raised to 6 over 6 factorial plus so on dx. Okay, so with this, we could have, um, you have this one. So this is x minus x cubed over 3 factorial plus 3 factorial because you have 3 times 2 factorial. Let's have this one. So you have uh, x raised to 5 over, this is 5 times 4 factorial. Okay. Minus x raised to 7 over 7 times 6 factorial plus so on. Plus c because there should be constant. So in this case, we could have, you have x minus x cubed over 3 factorial plus x to the fifth power over 5 factorial minus, it should be minus. minus x raised to 7 over 7 factorial plus so on, um, plus c, which is actually equal to, this is actually sine x. So you have sine x plus c. So the same idea applies to definite integrals. For example, direct integration, we have, let's say you have the integral of dx over 1 plus x squared from 0 to 1 is just equal to the arctangent x, which is, okay, from 0 to 1 would be equal to the arctangent minus tangent tangent. You have tangent 0, which is equal to uh, yun lang. Which is equal to uh, pi over 4 minus 0, which is equal to pi over 4. So we can still show, or we will show that pi over 4 is equal to 1 minus 1/3 plus 1 over 5 minus, it should be minus, sorry. So minus 1 over 7 plus so on. So if that would be the case, then you could have the integral of dx over 1 plus x squared from 0 to 1 would be equal to this one. So you have 1 minus 1/3 plus 1 over 5 minus 1 over 7 plus so on. So if you have this one, this would be, okay, so if we're going to get the interval, not the interval, the derivative, that would be equal to, you have x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th power over 7 plus so on. So this would be just equal to 1 minus 1/3 plus 1 over 5 minus 1 over 7 plus so on. Okay, so the preceding computation are justified by the following theorems. So the theorem of this one, integral power series. Suppose that the function f is represented by a power series in x minus x sub 0 that has a non-zero radius for convergence r. That is, the f of x is equal to the summation of c sub k times you have the quantity x minus x sub 0 raised to k from 0 to infinity at the interval x greater than x sub 0 minus r but less than x sub 0 plus r. If the power series representation for the function is integrated term by term, then the resulting series rather has the radius of the convergence r and the convergence to an antiderivative of the f of x on the interval x of 0 minus r to x of 0 plus r. That is, the integral of f of x times dx is equal to the summation of the integral c sub k over x plus 1 times the quantity x minus 0 raised to the power of x plus 1 from 0 to infinity at the interval x greater than x sub 0 minus r but less than x sub 0 plus r. If the alpha and beta are points in the interval x sub 0 minus r to x sub 0 plus r, and if the power series representation of the function is integrated term by term from alpha to beta, then the resulting series converges absolutely on the interval x sub 0 minus r to x sub 0 plus r, and the derivative of f of x dx from alpha to beta is equal to the summation of the quantity, the integral of c sub k times the quantity x minus x sub 0 raised to k dx from alpha to beta at k equals 0 to 8. So power series representations must be a Taylor series. For many functions, it is difficult or impossible to find the derivatives that are required to obtain the Taylor series. So, for example, to find the Maclaurin series for, let's say, oops, you have 1 over 1 plus x squared. Okay, so to find the Maclaurin series for 1 over x plus x squared directly would require some tedious derivative computations. A more practical approach is to substitute negative x squared for x in the geometric series. You have uh, dito na lang. You have 1 over 1 minus x, which is this is actually taken from the previous discussion that we have. 1 over 1 minus x is just equal to 1 plus x squared plus x cubed plus x raised to 4 plus so on. Okay, in the interval x greater than negative 1 but less than 1. So to obtain this problem, you have 1 over 1 plus x squared. Substitute. So you have that's equal to 1 minus x squared plus x raised to 4 minus x raised to 6 plus x raised to 8. However, there are two questions of concerns with this procedure. The first one is where does the power series that we obtain for 1 over the quantity 1 plus x squared actually converge to 1 over 1 plus x squared? And the second question would be, how do we know that the power series that we have obtained is actually the Maclaurin series for 1 over the quantity 1 plus x squared? The, hmm, the first question is easy to resolve. Since the geometric series converges to 1 over 1 minus x if the absolute value of x is less than 1. The second series will converge to 1 over 1 plus x squared if the absolute value of negative x squared is less than 1 or the absolute value of x squared is less than 1. However, this is true if and only if the value of x, the absolute value of x is less than 1. So the power series we obtain from the for the function 1 over 1 plus x squared converges to this point if x is greater than negative 1 but less than 1. The second question is more difficult to answer and lead us to this problem. Suppose that the function f is represented by a power series in x minus x sub 0 that has a non-zero radius of convergence. What relationship exists between the given power series and the Taylor series for f about x equals x sub 0? To answer this problem, um, the answer is they have the same. Okay, basing on this theorem, if a function f is represented by a power series in x minus x sub 0 on some open interval containing x sub 0, then the power series is the Taylor series for the function f about x equals x sub 0. Okay, so let's have an example. Find the Taylor series for the given function about the given x sub 0. Okay, so you have e raised to negative x squared, where x sub 0 equals 0. So the simplest way to find the Maclaurin series for e raised to negative x squared is to substitute negative x squared for x in the Maclaurin series e raised to x. So for the solution, okay, so we let um, x negative x squared to be in the x in the Maclaurin series e raised to x, which is from the previous discussion, e raised to x is equal to 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial plus so on, which is, okay, if we are going to substitute the x to uh, negative x squared, then we can obtain that e raised to negative x squared would be equal to 1 minus x squared plus x to the fourth over 2 factorial minus x raised to 6 over 3 factorial plus x to 8 over 4 factorial plus so on. Or not plus, minus so on. Since um, this this series converges for all values of x, uh, the series e raised to negative x squared is also converges. Okay, next. Uh, the same instruction, but in this case, we have the natural logarithm of x, where x sub 0 equals 1. So we begin with the Maclaurin series for the natural logarithm of the quantity 1 plus x. So from the previous example that we had, okay, previous discussion, we have the natural logarithm of 1 plus x would be equal to x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus so on. In the interval x greater than negative 1 but less than 1. So substituting x minus 1 for x in the series, we have the natural logarithm of 1 plus you have x minus 1 which will give us to the natural logarithm of x, which is equal to, you have the quantity x minus 1 minus the quantity x minus 1 squared over 2 plus the cube quantity of x minus 1 over 3 minus the quantity x minus 1 raised to 4 over 4 plus so on. Okay, so since the original series converges when x greater than -1 but less than or equal to 1, the interval of the convergence, which is this one, okay, the interval of convergence will be, you have, okay, the interval of convergence would be equal to x greater than -1 but less than or equal to -1. Wrong. X minus 1. X minus 1 should be greater than -1 but less than or equal to 1. Okay, so 1. Which is actually the same with x, because you have -1. So you have x is less than 0 but greater than, x is greater than 0 but less than or equal to 2. Okay, so let's have this one. Uh, find the integral of e raised to negative x squared from 0 to 1. E raised to the power of negative x squared dx from 0 to 1. Okay, so we actually know from the previous example, e raised to negative x squared is equal to 1 minus x squared plus x to the fourth over 2 factorial minus x to the 6 over 3 factorial plus x to the 8 over 4 factorial minus so on. Okay, therefore, we could have the integral of e raised to negative x squared dx from 0 to 1 would be equal to the integral of this one, 1 minus x squared plus um, x to the fourth over 2 factorial minus x raised to 6 over 3 factorial plus x raised to 8 over 4 factorial minus so on dx from 0 to 1, which is equal to, okay, getting the integral of this one, you have x minus x cubed over 3 plus x to the fifth over 5 times 2 factorial minus x raised to 7 over 6 times 3 factorial. Uh, Not 6, it should be 7. Sorry. 7 plus uh, x raised to 9 over 9 times 4 factorial minus so on. Okay, from 0 to 1, which is substituting, you have 1 minus 1/3 plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus so on. Okay, and if we are going to simplify that one from the previous discussion that we had, this series is just equal to the summation of the quantity negative 1 raised to k over the quantity 2k plus 1 times k factorial from 0 to infinity. Okay, so we have now the integral. So let's have another example. Find the first three non-zero terms in the Maclaurin series for the function f of x is equal to e raised to negative x squared times the arctangent x. So in this case, using the series for e raised to negative x squared and the arctangent x, okay, from the previous examples that we had, we could have this one as uh, e raised to negative x squared arctangent x would be equal to 1 minus x squared plus x to the fourth over 2 minus so on times x minus x cubed over 3 plus x to the fifth over 5 minus so on. So multiplying this one, so 1 times x, you have um, x. Then you have distribute. This is actually this distribution. So if you are just going to distribute this one, you could have minus what's this? So you have negative x cube minus x cube over 3, that is minus 4 third x cube plus you have x to the fifth over 2, the other one is x to the fifth over 3, and you have x to the fifth over 5. Okay, so that's 2, 3, 5, okay, so 31 over 30 x to the fifth. Okay, so on. Minus so on. Okay, so that's it. That's the answer. Okay, so let's find the first three non-zero terms in the Maclaurin series for tangent x. So for this case, using the first three terms on the Maclaurin series, since this is tangent x, we are going to use the identity of tangent x. So here, the tangent x is just equal to sine x over cosine x, which we have the series of sine x and cosine x. So that's equal to, you have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus so on over, you have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus so on. So we are just going to divide the two series, the two, yes, the two series, using long division. Okay, so in that case, you have x divided by 1, that is x. Mhm. Plus, uh, you have negative x cubed over 2, and then you have x to the fifth over 24. Okay, okay, x cubed over 3. Uh-huh. Then you have x cubed over 3 divided by 1. That would be, I don't know, x over 0. So plus 2x to the fifth over 15 plus so on. Just use the long division. Okay. Just something like this one. Uh, x minus x cubed over 3 factorial plus x to the fifth over 5 factorial divided by, this is minus so on, divided by 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus so on. Minus so on. You do... Okay, that's correct. So in other words, the tangent x is just equal to this one. Okay, so this is tangent x. Okay, so that's how we are going to have the first three non-zero terms of the Maclaurin series for tangent x. Okay, that's all for today.